Down through the ages, people have gathered herbs and boiled them to extract their flavor. Even today, a simple everyday example of extraction is the coffee pot. Boiling water percolating through the freshly ground coffee beans extracts from the beans the oils and soluble compounds that produce the well-known flavor of a cup of coffee. This example involves the exchange of material from a solid, the ground beans, to a liquid, the coffee. In addition, many extractions involve the transfer of material from one liquid phase to another liquid. As an example, clothing stained by oil can be cleaned by an application of cleaning fluid. This is extraction of a liquid, the oil stain, by another liquid, the cleaning fluid. Liquid-liquid extractions involve the separation of a compound from a mixture based upon the distribution of the compound between two immiscible liquid phases. For example, when bromine is dissolved in water, the aqueous solution is brown. When chloroform is added to the bromine-water mixture, the colorless chloroform settles to the bottom because it is denser than the water. If the solutions are shaken together and then allowed to resettle, the two liquids again separate into distinct layers. The bottom layer is still chloroform. However, it is now a red-brown color because of dissolved bromine. The water, or aqueous layer, is not as brown as it was before because some of the bromine has been extracted into the chloroform in which it is more soluble. It is possible to determine how much bromine is in each layer and then determine the distribution of the bromine between the two immiscible solvents. The ratio of the amount of bromine in water to the amount of bromine in an equal volume of chloroform is the partition or distribution coefficient. This coefficient is a measure of the relative solubility under a given set of conditions of a solute, in this case bromine, in two immiscible solvents, in this case water and chloroform. It is possible to predict the solubility of solutes in solvents to some extent. Nonpolar solutes, such as covalent substances which contain only carbon, hydrogen, and a halogen, tend to dissolve in nonpolar solvents such as benzene, carbon tetrachloride, or pentane. Polar solutes, such as salts of the organic acids and bases, tend to dissolve in polar solvents, such as water. This is the well-known solubility rule that like dissolves like. However, very often in an extraction, the organic solute is slightly soluble in the aqueous phase, and some will remain in this phase. In order to increase the efficiency of the extraction, the solubility of the organic compound in the aqueous solution can be decreased by adding sodium chloride or sodium sulfate to the aqueous layer. This procedure, known as salting out, creates a more favorable distribution coefficient for the desired extraction.
Extractions are often carried out in the laboratory using a separatory funnel. This pear-shaped funnel is closed at the bottom with a stopcock, and at the top by a glass or plastic stopper. The narrow neck of the funnel at the bottom helps to separate the two phases at the meniscus. The funnel's size should be chosen so that the combined volume of the solution to be extracted and the extracting solvent fills the funnel 1/2 to 2/3 full. The airspace that remains is necessary to make sure the layers are broken up and dispersed when the mixture is shaken. The stopcock of the separatory funnel may be lightly greased if it is glass to make sure it will turn easily. Excess grease should be avoided because the grease dissolves in the organic solvent and will contaminate the product. The separatory funnel is placed in a ring stand, and a beaker is placed underneath it in case any liquid leaks out of the funnel. Before adding any solution to the separatory funnel, make sure the stopcock is closed. Then the solution to be extracted is poured through a short stem funnel into the separatory funnel. Next, extracting solvent is added to the solution in the separatory funnel. If the stopper has a ground glass joint, it should be moistened with water to prevent the escape of organic solvent and to prevent the stopper from sticking. The separatory funnel is stoppered. The top of the funnel and stopper are grasped tightly with one hand, and the funnel is lifted from the ring stand. As soon as the funnel has cleared the ring stand, the other hand is placed around the stopcock to prevent it from falling out. Repeating this procedure, immediately after removing the funnel from the ring stand, the tip of the funnel is carefully and slowly raised 45 degrees above the horizontal. Never point the tip of the funnel toward people. The stopcock is held in and open to release the pressure of the solvent vapors. The stopcock is then closed and the funnel is turned upright. This procedure of turning the funnel over, opening the stopcock, and turning the funnel down is called venting. The funnel should be vented several times. If it is not vented, the pressure of the solvents may build up and pop off the stopcock or stopper. After the funnel has been vented, the stopcock is closed and the funnel is shaken vigorously for 10 to 30 seconds. The funnel should be vented again and placed in the ring stand. The stopper is removed and the layers allowed to settle until a distinct phase boundary forms between the two layers. The stopcock is opened slowly and the lower liquid layer allowed to drain through the tip into the receiving vessel. When the phase boundary is just above the stopcock, it is closed. A gentle swirling of the funnel in the ring stand allows any droplets that have adhered to the funnel walls above the lower phase during the draining to settle into the lower phase. The liquid is allowed to drain through the tip into the receiving vessel until the phase boundary is in the middle of the stopcock. The stopcock is then closed. The layer remaining in the separatory funnel is then transferred to a new receiving vessel by pouring it out the top of the separatory funnel. At the completion of the extraction, usually one layer, the one not containing the desired compound, is discarded. In the case of the extraction of bromine from an aqueous solution by chloroform, shown earlier, the chloroform was denser than the water and formed the lower layer which contained the bromine. Only the upper aqueous layer would be discarded. However, if a large amount of material is transferred from one phase to the other during an extraction, the relative densities of the original phases may change. That is, the phase initially at the bottom of the separatory funnel is on top after the extraction. Therefore, it is essential to know which phase is which before either is discarded. If the volumes of the two phases are substantially different, then one can distinguish and identify the phases. However, because of the shape of the separatory funnel, the lower layer may appear to be larger than it actually is, and the apparent volumes may be deceptive. In these cases, identification of the nature of the layers can be carried out by a simple test if one phase is aqueous. A few drops of the layer in question are placed on a watch glass and water added. If the water is miscible with the layer being tested, then it is the aqueous phase. If the water is not miscible, the layer is the organic phase. Although this might seem obvious, care should be taken not to accidentally discard the layer containing the desired compound. Both in student laboratories and research laboratories, many products have been thrown away by mistake. Once the separated phase containing the desired compound is obtained, it can be purified. If the material is in the organic phase, there may also be some water dissolved or suspended in it. This water can be removed by adding an appropriate drying agent. The choice of the drying agent depends on the nature of the solute. Because some drying agents are slightly acidic or basic due to the hydrolysis of their salts, care must be taken to choose one which will not react with the solution of the compound that has been extracted. In this case, anhydrous sodium sulfate is added to the separated organic layer, and the mixture is left to stand for a few hours.